Hello and welcome to my EECS 497.2 final project presentation. For my project, I chose to do a simple hex calculator design. This is an overview of what I will be presenting. I have a description of the design methodology, followed by a high-level description and specification for the design and test bench. I'll walk through the schematic detailing the individual blocks for both the design and the test bench, and wrapping up with the test results. I'll also spend a few minutes on potential next steps and some reference slides. For this project, I decided to draw on concepts I learned in this class. I decided to do an HDL high-level behavioral design of a simple hex calculator using SystemVerilog. The circuit is hierarchical, meaning that I have a top-level circuit that uses several sub-circuits. I used the ALU from homework assignment number 6 as the starting point for the design, and I also used the self-checking test bench from assignment number 5 as a starting point for my test bench. This is a description of the design. It's very high level. The calculator inputs are 2 unsigned 8-bit operands and 1 3-bit opcode. The output is a 16-bit result depending on the inputs and the opcode. The test bench provides the inputs to the calculator and checks the results. The input to the test bench is a text file containing test vectors, and the outputs are the results of the test, either printed to the screen or to a file. These are the specifications for my design. The calculator will get its inputs from a test file, and it will be able to perform basic arithmetic functions, addition, subtraction, multiplication, and division. It will also have some error handling capabilities for division by 0 and also to be able to flag an illegal opcode state. The specs for the test bench are also listed here. It needs to be able to read in a test vector file with up to 200 vectors. It also has test vector readback capability, meaning it will write what it just read back to a file. This is useful for debug purposes. It provides the stimulus for the inputs to the calculator. It has also self-checking capability by comparing the actual output with the expected value. And lastly, it will display the results on the screen as well as write them to a text file. This is the opcode table for the 4 operations. That last code, X11, is not a legal code. As you will see in the design, it is actually the error state code. This is the hex calculator schematic diagram. You might recognize the general architecture from the ALU in problem set 6. I wanted to reuse this design because it uses the same data bus for addition and subtraction, and I already had this basic structure working. Some of the modifications are the bit extender for the adder subtractor. Those are blocks ZX1 and ZX2. And I replaced the AND and the OR functions with the multiply and divide functions. And I also added the error handling circuitry. The next couple of slides go into detail on the various blocks, starting with this add-subtract circuit. It's basically the same circuit as in the book with the addition of the bit extenders at the input. I found this to be the easiest method to handle the expansion to the 6-bit output properly. The circuit uses the F2 control bit to decide if the operation is addition or subtraction. If it is a 1, the circuit will get the 2's complement of B in and add it to A in. The output will be in 2's complement if A is less than Bn. This is the multiply-divide circuit. The multiply circuit is pretty straightforward and not very interesting. It's a high-level function that simply takes the two 8-bit inputs and outputs a 16-bit product. The divide block is comprised of two high-level functions. The main divide function places the quotient of Bn divided by An on the lower 8 bits of the data bus, and a modulo function is used to compute the remainder, which is placed on the upper 8 bits of the data bus. The table describes how the answer is constructed. The circuit will force the divisor to 1 if An equals 0. This is not necessarily essential for the operation of the circuit, but it will force the quotient to a known state in this situation. Next is the error handling circuitry. The divide by 0 is detected when the opcode bits F0 and F1 and An is 0. The output of the OR gate is inverted and fed back to the bit extender OX1 to form the error code FFFF. MUX3 forces the output MUX to select the error input, and then the error code will be placed at the output. The other error that it will detect is if the illegal opcode is selected for any other operation. Then the error code at the output of OX1 will be FFFE, and it will be selected by the output MUX. The next couple of slides describe the test bench I used. This is a high-level block diagram of the test bench. The circuit will read and decode the test vectors from a text file. The design will take up to 200 vectors, but can easily be modified to accept more. I also added a readback file capability. This was to help me debug some issues I was having with not decoding properly. I'll talk more about that on a later slide. The test bench will pass the input codes to the DUT and accept the output back to compare with the expected value. The test results will be printed to the screen as well as to an output test file. This shows the test vector file, which is on the left. This is the file that the program reads, and on the right is the file that is read back and written to a separate file. I have an example of the syntax for the test vector on the slide. I separate each field with an underscore to make it easier to read. The first two fields are the A and B inputs. The third is the opcode. And the last field is the expected output, and these obviously are all in hex values. In the example shown, the first vector should flag an error since it is a divide by 0. I should mention, as I say in the notes on the slide, each hex number is 4 bits. I had a bug when I first tried this because my opcode is only 3 bits. And it was not deconstructing the vector properly because I did not take this into account originally. The underscores are actually ignored by the program, which makes it convenient. This shows the output text file from the test bench. I intentionally put errors into the test vectors to demonstrate how this works. Most of the fields are pretty self-explanatory. The pass-fail test status refers to the success of the output, meaning if the output of the calculator is equal to the expected output from the test vector, then it is a pass. So on test number 7, it failed because the test vector said the expected output was 0000, but the actual output was FFFE, the error code for an illegal opcode. This was an intentional error that I put in there just to demonstrate this operation. This slide is just a screenshot of the output displayed as the simulation is running. It contains the identical information as the output text file. Note at the bottom of the test, at the end of the simulation, a summary of the test is printed. Here it's 102 tests completed with 7 errors. This is a screenshot of the output waveforms, which is another way to view the results. I think the waveform window is more useful during the debug state because there are so many cases that are tested that it would be difficult to find them in this format. This is basically a wish list of some of the steps I could take if time permitted or if I was to continue with the project. I think this simple design was a good project to help me think logically to get through the necessary steps to complete a working model from idea to design to test. Next steps for me would be to start to migrate towards hardware where I could accept inputs from the keyboard, output results to some kind of display. I would also need to start on the logic level design of the blocks, and it would be good to be able to simulate the design and hardware using an FPGA. And next steps, of course, to add more functionality. These are references. More of my research came from the book or Stack Overflow. Invariably, each time I did a Google search for something, they were the top 5 hits. If an answer was to be found, Stack Overflow would have it. I used ModelSim for the simulations, a free schematic capture tool called LogSim, and Draw.io for the diagrams. This was my starting point that I referred to. This ALU and test bench is from the book. The next couple of slides contain the source code. I'm not going to go into detail on any of these. They're very heavily commented, so you can spend some time and go through them in the materials that I'll post. This is the test bench, probably the most complicated piece of this design. This is the top level. I mentioned that it's a hierarchical design, and you can see here is the top level calling all of the individual modules. And these are all the modules. As I said, the code is pretty well commented, so you can, or if not, they're pretty straightforward, and you'll be able to go through them in the materials that I'll provide. Thank you for watching my presentation, and bye-bye.